Okay. So welcome to the midterm exam review. Again, you can find me on YouTube at Andrew Scarf, and I will post this recording afterwards. So these questions have been pulled from previous finals and midterms that are available to you. They're provided in this review as practice problems, but they may not be representative of the distribution of questions. You're responsible for the content that has been taught in this class and is outlined in your syllabus. So again, we'll post this on YouTube, so it's available to you. So any kind of distribution of this is prohibited, but it will be made available to you on YouTube. And again, we're going to focus on content prior to the midterm in this review session. So the way this review session is going to work is I'm going to put a question on the screen. I'm going to give you a few minutes to try the question on your own. I encourage you to try the question on your own, and then we will solve it together. But the expectation is that I will give you 3 to 5 minutes, depending on the intensity of the question. You will try it yourself. So have a pen and paper and calculator ready. And you'll give yourself some practice solving those questions. So here is our first question. So I'll give you 3 or 4 minutes here. Try it on your own, and then we'll take it up together. Okay, so that was about 3.5 minutes. So I'm just going to go ahead and start reading the question. If you're doing well on your own, then keep going. Otherwise, we'll solve it together. So a mining company explores a site for copper and zinc using exploratory drilling to obtain samples. The probability that the sample contains copper is 0.6, and the probability that the sample contains zinc is 0.5. The probability that a sample contains both zinc and copper is 0.4. So what is the probability that a sample containing zinc also contains copper? Well, here we have the probability of copper given zinc. So the probability the sample contains zinc also contains copper. So probability of copper given zinc is equal to the probability of copper and zinc divided by the probability of zinc, right? This is your basic conditional probability. So the probability of copper given zinc is equal to the probability of copper and zinc divided by the probability of zinc, where the probability of copper and zinc, so the probability, let's just get our pencil out here. The probability that it contains both zinc and copper is 0.4, and the probability that it contains zinc is 0.5. So 0.4 divided by 0.5 gives us a probability of 0.8. So is the presence of copper and zinc in the samples 1 mutually exclusive and 2 independent? State your reasons clearly. Well, it's mutually exclusive if the probability of zinc and copper is equal to 0, meaning that the two events don't occur at the same time, right? That's what mutually exclusive means. But to the extent that the probability of zinc and copper is equal to 0.4, right? That's told to us in our question. We know that these two events are not mutually exclusive. So we've answered number 1 here. So they are not. We then asked ourselves, are they independent? Well, they're independent if the probability of copper is equal to the probability of copper given zinc. But in this case, the probability of copper is 0.6, and the probability of copper given zinc is 0.8. So therefore, they are not independent of each other. In other words, knowing that zinc is there, given zinc, gives us some information that is relevant to our estimation of the probability of copper. So because 0.6 does not equal 0.8, they are not independent of each other. And then what is the probability that 5 consecutive samples contain either copper or zinc? Well, we can do this as the probability of copper or zinc is equal to the probability of copper plus the probability of zinc minus the probability of copper and zinc, right? In other words, we have you can imagine that we have some kind of Venn diagram here where we have copper and zinc, and we have some instance where they occur at the same time. So if we're asking ourselves about the probability of A or B, we have to subtract the probability of A and B together. So the probability of copper or zinc is equal to the probability of copper plus the probability of zinc minus the probability of copper and zinc. And this is exactly this kind of shaded region that we just created in our Venn diagram there. So what do we get? We get 0.6, which is the probability that the sample contains copper, plus 0.5 minus the probability that it occurs in both samples, which gives us a value here of 0.7. But the probability that we get 5 samples in a row that contain probability or copper or zinc is simply equal to the probability of copper or zinc to the power of 5, right? In other words, we're writing 0.7 times 0.7 times 0.7 times 0.7 times 0.7, right? This is what this equals. When working on your calculators, it's good to know how to use this exponent function, because if you're typing in 0.7 times 0.7 times 0.7 times 0.7, the likelihood that you make a mistake is quite high. So try and get familiar with your exponent function on your calculator. So when the probability of copper or zinc is 0.7, the probability that we get 5 samples in a row that contain copper or zinc is equal to 0.16807. Okay. Here's our next question. This one's a fun one, so I'll give you a little bit of extra time because it takes some reading. But as always, we will take it up together. Okay, so that was about 5 minutes. So let's go ahead. So Baffin Bay, located between Canada and Greenland, is being explored for oil and natural gas. First energy company conducts a geological survey, and if the data looks promising, it starts drilling. A recent survey of one area cost $65 million and indicates that drilling will be successful with a probability of 0.21. Drilling costs are 0.32 billion with a probability of 0.7 and 0.65 billion with a probability of 0.3. Due to the fact that the survey does not identify the geological structures precisely, if the drilling is successful, the revenue from the sale of oil and gas will be 2.7 billion with a probability of 0.75 and 3.2 billion with a probability of 0.25 due to uncertainty about the future prices at which the company can sell the oil and gas. And we have the following 4 questions. So what is the expected cost of drilling? So let's start there. So our expected cost of drilling, or otherwise known as our expected value. So our E of X is equal to, let's break down these kind of nastier looking symbols. This is just sum of value of Xi, so all values of X times the corresponding probability of X. So we had an expected drilling cost of 0.32 billion. And we're told that this occurs with a probability of 0.7 and another drilling cost of 0.65 billion. And we're told that this occurs with a probability of 0.3. So 0.32 billion times 0.7 plus 0.65 billion times 0.3. Ultimately, we end up here with an expected drilling cost of $0.419 billion. Now, important for this, when you're thinking about your expected value of any particular situation, what you'll notice here is that if we take the sum of these two probabilities and we add them together, 0.7 plus 0.3 is equal to 1.0. Okay, so whenever you're doing the expected value calculation, always make sure that the sum of your probabilities adds up to 1. If it doesn't add up to 1, you're missing a probability somewhere, and you're going to have to go back through and check to see what you're missing. Okay? So this is our expected drilling cost, of course, in billions of dollars, so fairly expensive. We're asked, what is the standard deviation of the cost of drilling in billions of dollars? Well, the first thing we're going to do here is we're going to calculate our variance, right? Remembering the relationship between variance and standard deviation, such that the square root of the variance is equal to our standard deviation. So let's start by calculating the variance of our drill cost. And all we're doing here is the sum of the observed value of x minus the expected value of x squared times the probability, right here, the probability that that event x occurs. So we have a drilling cost of $0.32 billion, right? Given to us in the question. We then subtract our expected value of $0.419 billion. We square that difference, and then we multiply by the probability that this event occurs, which we're told in the question occurs with a probability of 0.7. We do exactly the same thing for our next observed value. So 0.65 billion minus the expected value squared times the probability that that event occurs, at which point we're going to get our difference here. And what we get here is 0.022869. This would be in billions of dollars squared, to the extent that we've squared our dollar unit here, but squared dollars doesn't make a lot of sense, so we'll just leave that off. We'll remember that we're working in dollars. So then we're going to look at what is the standard deviation, since that's what the question is asking us. So we remember that the square root of the variance is equal to our standard deviation. So our standard deviation of our drill cost is equal to the square root of the variance of our drill cost. So the square root of 0.022869, to which we get a standard deviation of drill costs to be $0.1512 billion. Right? Really important that when you get to the standard deviation phase, that you are specific about your units, right? We want to know what units that standard deviation is in. And to the extent that our dollars were represented in billions of dollars throughout, we'd want to keep that there as well. Okay, so really important remembering that relationship between your standard deviation and your variance. Could you do this all in one step simply by taking the square root of the variance? Yes, you could. I prefer to break it out into multiple steps, where I first calculate the variance and then I calculate the square root of the variance. I find that it's less error prone when you do it that way, but of course, it is your own personal choice of how you'd like to solve for this question. But effectively, the same basic steps would apply, just whether or not you're breaking it out into multiple steps or not. Then we're asked, what is the expected revenue in billions of dollars? Well, another way of looking at this is just your expected value, but in this case, we're talking about revenue. So again, we're taking the sum of the observed values of X multiplied by their corresponding probabilities of X. And we're told that the probability that is successful is 0.21, right? This is the trick of this question. We're told that drilling will be successful with a probability of 0.21. So in every instance, while the revenues may be reflected with a probability of 0.75 and a probability of 0.25, we have to account for the fact that drilling is only successful in 21% of cases, or a probability of 0.21. So we have to factor that in to our question. So our probability that we are successful. So 2.7 billion times the probability of 0.75 times the probability that it's successful of 0.21. We do the same thing, 3.2 billion with a probability of 0.25 multiplied by the probability that the drilling is successful in the first place, to which we would get an expected revenue of $0.59325 billion. Right? Or $593.25 million, right? Then we can ask ourselves, what is the expected profit in billions of dollars? Well, our expected profit is simply equal to revenue minus cost. And as any business student, you would know this as revenue minus cost is your profit. But we have to pay attention that we cannot just simply take the expected value that we calculated up here in question 1. Why can't we do that? Well, in doing that, we didn't account for the fact that there is a $65 million drilling cost associated with any one of these wells. So what we have to account for in our expected cost is equal to the expected drill cost, that is the 0.419 billion, plus the expected survey cost. And in this case, they just told us what the survey cost is. The survey cost is $65 million or 0.065 billion. To the extent that we're working with billions of dollars for our drilling cost, we may as well just convert the 65 million into billion, right? So we've just moved the zeros a little bit there, to which we get our expected cost then of 0.419 billion plus 0.065 billion, which gives us an expected cost of $0.484 billion. From there, now that we have our cost, we can calculate our profit. So simply revenue minus cost. So we take our expected revenue that we calculated here in question 3, and we then subtract our expected cost, to which we get a profit of $0.10925 billion. Okay, so this is a little bit of a tricky question. There's no question about it. Probably the trickiest part of this question are two things. One, and it's right here in the first line, right? So the first line of this question that tells us that we have a survey cost of $65 million that we need to account for, and the second being that the drilling is only successful with a probability of 0.21, right? And it's intuitive to assume that you're not going to make any money if the drilling isn't successful, right? You've just drilled an empty well. Okay. Let's move on to this next question. Again, I'll give you some time, and we'll go from there. Okay, so let's take a look at this question. So the company Innova manufactures small gasoline engines in 3 factories, M1, M2, and M3. That's just the name of our factories. All engines are tested before delivery and are declared to be acceptable, defective with minor defects that are repairable, or unacceptable. That is, there are major issues and it is not repairable. The following table provides the number of engines for each category of production for the 3 factories. Well, it says factory, but it should say factories. So let's just take a look at this table before we even get to the questions. Let's look at this table, and what do we have here? We have what is called a contingency table, right? And with our contingency table, what are we dealing with? Well, we're dealing with categorical variables, right? So those that can be counted, but we have a categorical variable here that we'll call like engine status. And we have a categorical variable right here that is just factories, right? Now, let's look at a few properties of our contingency tables that are important to know. So first, in our total box, we notice we have a total of 1,400, right? And I don't have a better word for it other than the total box, so we'll just ride with it, right? 1,400. So what do we notice about this total box? Well, the sum of our rows must equal this total box. So 1155 plus 160 plus 85 gives us 1,400. Alternatively, 540 plus 380 plus 480 gives us 1,400. Now, within our contingency table, 450, or let's do this one. 60 plus 40 is 100 plus 60 equals 160. Right? We go down the column. 450 plus 60 is 510 plus 30 gives us 540. Right? So this is the sum of our row in column M1, and this is the sum of our columns for row 1. Okay, so if you're missing information in a contingency table, using the properties of the contingency table, knowing that the sum of the columns must equal the sum as they appear in the margins, and the total is going to be the same as the sum of our rows and the sum of our columns. Okay, that should be second nature to you at this point, so we won't spend more time talking about that. But let's get into the question. So what is the probability that an engine is defective or that it comes from factory M2? Well, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So the probability that it's defective or comes from factory M2 is equal to the probability that it's defective, which we see here is 160 divided by our total. So 160 engines in total are produced, plus the probability that it comes from factory M2, which is 380 divided by 1,400, minus the probability that it's defective and M2, right? Really important that we subtract this instance here. This is our joint probability. So 40 over 1,400, right? In case you didn't pick up on that, let's just look at this for one extra second here. So we have what's called our joint distribution, and then we have what's called our marginal distributions, right? Also known as joint probability and marginal probability once we divide it by our total. Okay, so what we get here then is 500 divided by 1,400, which gives us a probability of defective or M2 to be 0.3571. Okay, what is the probability that an engine is defective and it's unacceptable? Well, the probability that it's defective and unacceptable is 0. Right? Now, why is it 0? These two events cannot happen at the same time. Right? The engine is either defective or it's unacceptable, but it is not both defective and unacceptable. Right? In other words, an engine cannot both be defective and unacceptable. Therefore, these are considered mutually exclusive events, at which case our probability is equal to 0. So knowing that an engine was produced by factory M3, what is the probability that it is defective? So this is our conditional probability here. So the probability of A given B is equal to the probability of A and B divided by the probability of B. So the probability that it's defective given factory M3. So we get 60 divided by 1400 divided by 480 divided by 1400, which gives us a final probability here to be 0.125. Okay. Knowing that events are disjoint, what is the probability that the event that an engine is manufactured at M1 or M2? Right? So disjoint, these events don't occur together, right? So it's either at M1, M2, or M3, right? These events do not occur together. They are disjoint. So knowing that the events are disjoint, what is the probability at M1 or M2? So we're talking about the probability of A or B. So the probability of A plus the probability of B, or in this case, M1 or M2. So we get the probability of M1, which is 540 divided by 1400, plus the probability of M2, which is 380 divided by 1400, which gives us a probability of 0.6571. Right? The other way that you could have approached this problem is saying, well, I can just do the probability of M1 or M2 is equal to 1 minus the probability of M3. Right? That's also appropriate. So is equal to 1 minus 480 divided by 1400, which will give you 0.6571. Okay, that's another way of solving it, using that complement rule. So what is the probability that an engine is produced by factory M1 given it's unacceptable, right? So we have this word given, right? So little kind of red flags, little alarm bells might be going off in our head, thinking that we might have some kind of conditional probability. So the probability of A given B, so the probability of A and B divided by the probability of B. So the probability of factory M1 given it's unacceptable is equal to the probability of M1 and unacceptable divided by the probability that it's unacceptable. Right? So the probability that it's M1 and unacceptable divided by the probability that it's unacceptable. So 30 divided by 1400 divided by 85 divided by 1400. Ultimately, you could simplify this and you could just say 30 divided by 85, which will still give you the same answer here of 0.3529. And then finally, what is the probability that an engine is unacceptable and that it was manufactured at either factory M1 or M2? Right? This question is definitely a little bit challenging. So we note that M1 and M2 are disjoint, meaning that they don't happen at the same time. So probability of A and B is equal to the probability of A plus the probability of B for disjoint events, right? Well, here we're asking what is the probability that the engine is unacceptable and that it was manufactured at either factory M1 or M2. So what we really are writing is the probability it's unacceptable and M1 or M2. So the probability of unacceptable and M1 plus the probability of unacceptable and M2. So the probability of unacceptable and M1 is equal to 30 divided by 1400 plus the probability of unacceptable and M2, which is 25 divided by 1400. Ultimately, the probability that it's unacceptable and from factory M1 or M2 is equal to 0.039286. Okay. Let's go to our next question. So here's our next question. I'll give you a few minutes to try it on your own, and then we'll try it together. Okay, so it is well known that the new generation of microprocessors have a low yield ratio in initial production batches. In other words, the percentage of defective microprocessors is high. In one such batch, 20% of the new microprocessors are defective. A small lot of 10 microprocessors was purchased at random from this batch, and we're going to calculate the probability that exactly 2 microprocessors are bad. So in this scenario, what we have is a binary outcome, right? The microprocessors are either good or they are defective, right? That's effectively what the question is asking us. So what this should cue in our mind when we're presented with an instance where we're trying to calculate the probability of a binary outcome is that we should be thinking about the binomial distribution, right? So here's our equation for our binomial distribution. So the probability that x is equal to x, so the probability that we have x number of successes, right? Keeping in mind that this is a discrete probability distribution, meaning that we're calculating the probability that it's exactly whatever x represents, number of successes. So in this case, we're saying that the probability that x is equal to 2 is equal to 10 factorial. That's the number that we're in our small lot, divided by 2 factorial. That's the number of processors that were bad, times 10 minus 2 factorial. In this case, a success would be finding a defective microprocessor. So we're going to say P is equal to 0.2, which means that Q is equal to 1 minus P, which is equal to 0.8. So we get 0.2 to the power of 2, right? This is our number of failures, or in this case, what we're letting P is our success, which would be finding a bad microprocessor, times 0.8 to the power of 10 minus 2. So then you go and you do, I recommend that you do this stepwise on your calculator. So we get 10 factorial divided by 2 factorial times 10 minus 2 factorial. Keep in mind that when you're punching this in on your calculator, you have to be conscious that you put brackets around this. Otherwise, your calculator will do the following. If you just type in 10 factorial divided by 2 factorial times 8 factorial, it will do 10 factorial divided by 2 factorial times 8 factorial, right? If you just punch it in your calculator without brackets. So this, let me just put a big X through that. That is wrong. This is 10 factorial divided by 2 factorial times 8 factorial, right? This is right. So be mindful when you punch that into your calculator. Ultimately, what we get here is a probability of 0.30198. So this is the probability of exactly 2 microprocessors being bad. Bit of a tricky question here because we typically associate bad with a negative outcome or Q, but in this case, identifying that the microprocessor was bad was in fact our positive outcome, or what we let P equal. So P was equal to 0.2 and Q equal to 0.8. Okay, calculate the probability that at least 8 of the microprocessors were good. Well, the probability that we have at least 8 good is equal to the probability that 2 were bad, that 1 was bad, or 0 were bad, right? That's effectively what we're saying. If there's at least 8 good ones in a batch of 10, either 2 of them were bad, 1 of them was bad, or none of them were bad, meaning that we either had 8 good ones, 9 good ones, or 10 good ones. In this case, good meaning not defective. So the probability of at least greater than or equal to 8 is equal to 10 factorial divided by 2 factorial times 8 factorial times 0.2 to the power of 2 times 0.8 to the power of 10 minus 8, 10 minus 2, which is to the power of 8. And we do this for each of these values. So the probability that 2 were bad, the probability that 1 was bad, and the probability that none were bad. Ultimately, what do we get? We get this probability here of probability that x is greater than or equal to 8 to be 0.67779. Okay. What would be the coefficient of variation for the distribution function for this experiment? In this situation, the same distribution function as the one for bad microprocessors applies. Well, our coefficient of variation is equal to our standard deviation divided by our expected value. For a binomial, we recall that our standard deviation is equal to the square root of n times p times 1 minus p, which is our SD is equal to the square root of n times p times q. We also remember that the variance is simply equal to n times p times q. So this relationship that the standard deviation is equal to the square root of our variance. So our standard deviation of x is equal to the square root of our variance of x still holds true. And we recall that to calculate our expected value for our binomial is simply n times p. Okay, so in this case, we're doing bad microprocessors or defective. So 10 times 0.2, we do this math and we get a coefficient of variation to be 0.63245. Effectively, our coefficient of variation represents the size of the standard deviation relative to the expected value or the spread of our observations. But for this question, we just have to be able to calculate it. The purchaser tests each of the microprocessors, each in turn, calculate the probability that the first defective microprocessor is discovered, happens to be the 10th tested. Okay, so the key to this question before we go to the answer is that we're asking the probability that the first defective microprocessor is discovered on the 10th tested. Okay, so the first one. So in here, we're going to apply our geometric probability equation. So the probability that x is equal to x is equal to q to the power of x minus 1 times p. So the probability that x is equal to 10, or that we have our first success on our 10th attempt, is equal to 0.8 times, 0.8 to the power of 10. That's our 10th attempt minus 1, times our probability, in this case, of success or finding a defective device to be 0.2, which gives us a probability that our first success is on our 10th try is equal to 0.02684. Okay, also not very likely that that happens. Okay. Let's try this question. This one is a bit long as well, so we'll give it a shot and then we'll take it up together. Okay, so the regulations for young drivers getting a probationary motor vehicle driver's license will be severely tightened in the coming months. Here are some relevant data giving accident statistics based on driving frequency. 15% of drivers have a probationary license and 85% have a regular license. In a given year, 10% of drivers with a probationary license are involved in an accident, whereas 2.5% of all drivers with a regular license are involved in an accident. The occurrence of the accidents for any driver from year to year can be assumed to be independent events, meaning that if you were in an accident last year, it doesn't necessarily increase the probability at which you have an accident the following year. Okay, so that it's year over year independent. So before we even go to start answering these questions, we can write out what we're given. So we're given the following information. So we're told that the probability of a probationary driver's license is 0.15. We're told that 85% of the people have a regular driver's license. So that's probability of regular driver's license. We're also told that in a given year, 10% of drivers with a probationary license holder are involved in an accident. So in other words, the probability of an accident given their probationary license holder is 0.1. And the probability of an accident given they are a regular license holder is 0.025 or 2.5%. So this is the information that we're given. Now, we can take this one step further because sometimes it helps to draw things out. So you might draw a decision tree that looks kind of like this, right? You don't need to call this start. I just did this because I was working in Microsoft Office in the PowerPoint and I just wanted to use the decision tree. But you'd probably start it like this. So you have the probability that they're a regular license holder versus the probability that they're a probationary license holder, right? So 0.85, the probability that they're a probationary license holder, 0.15, the probability that they're a probationary license holder. We're then told, let's clear some of these markings just to make it easy. We're then told that we have the following information. So we're told the probability of accident given their probationary license holder is 0.10, right? So that's what is reflected right here. And we can also then say that the probability of no accident given probationary license holder is equal to 1 minus the probability of accident given probationary license holder, which is equal to 1 minus 0.10, which is equal to 0.90. Right? So 0.90 right here, 0.10. We're also told that the probability of an accident given a regular license holder is 0.025 or 2.5%. So the probability of no accident given regular license holder is equal to 1 minus the probability of an accident given their regular license holder, which is equal to 1 minus 0.025, which is equal to 0.975, right? In other words, right here. So in drawing our decision trees, what is important to remember is that the sum of the probabilities at each either state of nature or decision node. So if we start right here, 0.85 plus 0.15 is equal to 1. Again, same thing, 0.1 plus 0.9 is equal to 1, and 0.025 plus 0.0975 is also equal to 1. So at each particular point, one of the outcomes are going to occur. So if we're standing right here, what's going to happen? Well, they're either going to have a regular license or a probationary license. Standing right here, knowing they have a regular license, they're either going to have an accident or not have an accident. If we're standing right here, knowing that they have a probationary license, they're either going to have an accident or not have an accident. So that's our basic decision tree. So now we can go ahead and answer our question. So for a randomly selected driver, what is the probability that in a given year an accident will occur? What is the probability that an accident won't occur? Well, let's just go back to our decision tree for just an instant, just a moment. So there's 2 times when an accident occurs. The first time is when they have a regular license and an accident occurs. The second time an accident occurs is if they have a probationary license and an accident occurs. Right? So those are the 2 types of accidents. They're either going to have a regular license or a probationary license. So all we're going to do here is multiply across our branches. So the probability probationary license times the probability of accident given probationary license plus the probability of regular license times the probability of accident given a regular license. So you just use the information that's right here for you. At which point we sum those values together and we get a probability of an accident to be 0.03625. From there, we can calculate the probability of no accident is simply 1 minus the probability that there is an accident, to which 1 minus 0.03625 gives us 0.96375. Right? Oftentimes students will ask, how many decimal points do I need? I advise holding at least 4. You'll notice that I have 5 here, but I would report at least 4. Of course, if your exam is multiple choice, then you're going to pick the most right answer. So if there's only 2 decimal points on your exam and you have an answer that looks like 0.96, this would be your right answer. But otherwise, I would, in my calculations, keep as many decimal points as I can to avoid a rounding error. Okay, so then calculate the probability that if there is an accident, the driver is a probationary license holder. So what we're asking is the probability of probationary license holder given there is an accident, right? So we can just scroll back here. So given they're a probationary license holder, what is the probability that there is an accident? So we're going to take the probability that they're a probationary license holder, which is 0.15, and we're going to multiply by the probability that there is an accident given their probationary license holder. And then importantly, we have to divide by the probability that there is an accident. And this is the probability that we calculated here in question A. Okay, so the probability of probationary license holder given there's an accident is 0.4138. Calculate the probability that if there is an accident, the driver is a regular license holder. Well, we can do exactly the same thing. So the probability of regular license holder given accident is equal to the probability of regular license holder times the probability that they have an accident given regular license holder divided by the probability that there is an accident, which gives us a final probability here of 0.5862. What you'll notice, though, is that the probability of regular license holder given accident is equal to 1 minus the probability of probationary license holder given an accident. So equals 1 minus 0.4138, which is equal to 0.5862. You could do one way or the other. You're obviously welcome to solve this either way. The advantage, I think, with the first way is that if you did make a mistake in question B, that mistake shouldn't carry forward into your calculation from C. So, choose your own adventure. But one way is a lot more dependent on your calculation from question B being right versus your question C. Okay, so then what is the probability that over a period of 3 years, a probationary license holder will have at least one accident? So we get the probability of no accidents, and this is just misspelled, so my apologies. No accidents in 1 year given the probationary license holder is equal to 1 minus the probability that they have an accident given their probationary license holder, which gives us a probability of 0.9 that they will not have an accident in a given year. So what we're asking is that the probability that there are no accidents in, this should say 3 years, given a probationary license holder is simply equal to 0.9 to the power of 3, right? The probability that they do not have an accident in 3 years, right? So 0.9 times 0.9 times 0.9, right? So 0.9 to the power of 3 is equal to 0.9 times 0.9 times 0.9. And then this should say 3 years again. So what we get here is that we get the probability of greater than or equal to one accident in 3 years given a probationary license holder is equal to 1 minus the probability of no accidents in 3 years given probationary license holder, which is equal to 1 minus 0.729, which gives us a probability of at least one accident in 3 years given probationary license holder to be 0.271. And then finally, what is the probability that over a period of 3 years, a regular license holder will be without accident? Well, we're just going to calculate the probability that they have no accident in 1 year, given that they're a regular license holder. So we get 1 minus the probability that they have an accident, given they're a regular license holder. So the probability that they have no accident in 1 year is 0.975. And then the probability that they are without accident in 3 years is simply equal to the 0.975, the probability of no accidents in 1 year to the power of 3. Now, why can we do that? We are told that from year to year, the probabilities are assumed to be independent. So all we're going to do is multiply those years together. So year 1 times year 2 times year 3, right? This is the probability of no accident in year 1 times the probability of no accident in year 2 times the probability of no accident in year 3. Okay. Let's give this question a try. So a large service depot has clientele of large companies with extensive computer equipment. The average number of service calls they receive every day over an 8-hour period is 3. They employ 3 highly trained technicians and other supporting staff. Each service call requires 1 technician for the entirety of the day on which they are called. So what is the probability on any given day there will be exactly 4 service calls? Well, when we see a question that's giving us something like a unit of time, so an 8-hour period, the expected number of calls is 3, at least immediately you should be thinking perhaps we're dealing with some kind of poisson distribution, right? Where poisson distribution is a continuous distribution and it's dealing with number of events per unit of time. So in any given day, where 1 day is equal to 8 hours, we expect to receive 3 calls in 1 day. So our value for lambda is just equal to 3, right? In other words, we expect to see 3 calls in one day. So our lambda is equal to 3, right? Lambda is what this Greek letter is called. So we have our probability distribution here for our Poisson distribution. It's a continuous probability distribution. So the probability that x is equal to x. Sorry, my apologies. It's not a continuous probability distribution. It's a discrete probability distribution. My apologies. That was me goofing. It is a discrete probability distribution. So the probability that x is equal to x is equal to e to the power of negative lambda times lambda to the power of x divided by x factorial. So the probability that we have exactly 4 service calls, so the probability that x is equal to 4 is equal to e to the power of negative 3 times 3 to the power of 4 divided by 4 factorial. Right? E is a naturally occurring value. It exists on your calculator. I'd get familiar with that if you haven't already. So again, our Poisson distribution is a discrete probability distribution that we can use to calculate the probability of exactly a certain number of events. So probability we have exactly 4 is 0.168. What is the probability that there will be more than 3 calls in one day so that these 3 technicians will not be sufficient? Well, lambda again is equal to 3 because we're still dealing with our 8-hour day. So lambda is equal to 3. So what we're asking is, what is the probability that we have more than 3 calls? So the probability that x is greater than 3, which is simply equal to 1 minus the probability that x is less than or equal to 3. All right. Effectively, we could have 4, 5, 6, 7, 8, 9, ... all the way to infinity number of calls in and out in a day. So it's not a viable solution to calculate it that way. So instead, we're going to use our complement here. So 1 minus the probability that x is less than or equal to 3 will give us the probability that x is greater than 3. So we just go through this and we do this for each value. So the probability that x is equal to 0, the probability that x is equal to 1, the probability that x is equal to 2, and the probability that x is equal to 3, right? Where x is equal to the number of calls in a given day. Unfortunately, there's no quicker way to do this. You just have to go through and do this with calculation by hand. And I just saw something here, so let me just take a look at something. E to the power of negative 3 times 3 to the power of 3. I'm just checking this. E to the power of negative 2 times 3 to the power of 2 divided by 2 factorial. So this answer here is actually, I've made a mistake. This is supposed to be e to the power of negative 2 times 3 to the power of 2. So if I go e to the power of negative 2 times 3 to the power of 2 divided by 2 factorial, this is equal to 0.6090. So 0.69. And again, I've made another mistake. No, I haven't made a mistake. I was right. E to the power of negative lambda. My lambda is equal to 3. We're good. So my apologies. I got turned around in my own equation.
e to the power of negative lambda. Our lambda is equal to 3, so that's all good. So my apologies, everybody. I got turned around a little bit. Hopefully that's okay. I went on autopilot perhaps for a second. The question is, can we subtract the probabilities and subtract 1? Yes. So you could sum these all together. So the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3, and then subtract from 1. You can absolutely do that if that is the way you'd like to go. So my apologies, folks. Let's hope that doesn't happen again. So then one day there will be no service calls in the morning and one technician will be allowed to take the afternoon off. In the remaining 4 hours of the afternoon, what is the probability that there will be more than 2 service calls in the afternoon so that the service depot will not be able to meet the full service needs with only 2 technicians? Well, we remember that we have to adjust our value for lambda here. So our 3 calls in 8 hours is then going to be equal to 1.5 calls in 4 hours. Okay, that's going to be our expected value. So our expected value, or our lambda, is equal to 1.5 calls in 4 hours. So the probability that we have more than 2 calls is equal to 1 minus the probability that we have 2 calls minus the probability that we have 1 call minus the probability that we have 0 calls. Right? And you can do the math and you can see the answers here. I'll also just say that just to follow up on that question, 1 minus P0 plus P1 plus P2 would also be an appropriate answer. We just have to remember that we have to do what's inside the brackets first and then subtract from 1. Okay, but if you do the same step, if you do that step, you will still get to the final answer here of 0.1912. Okay, and then in our last question that we're going to do today, because we're running out of time, this one is going to take a little bit of reading first, so I'm going to give you a little extra time. So I'll give you about 5 or 6 minutes, and then we'll take it up together, and then we will wrap up. Okay, so Karen is starting a career as a professional wildlife photographer and plans to photograph Canadian geese at one of the starting grounds during their migration in northeastern Manitoba. She booked a place in the hide at the edge of the lake and plans to photograph the geese as they land on the water. For the price of a room in the Hilton, $200 per day, she gets a spot on the wooden bench shared by other photographers, a muddy floor, a bracket to mount her telephoto lens, a tent to sleep in, and delicious meals of freshly caught fish. A lot of information there, not a whole lot that's useful, but anyway. Last year, during a stay of 3 days in the hide, she got 2 shots worth $5,000 each. She regards this as typical for this time of year, although good shots happen at random each day and is independent of others. To establish her reputation, Karen only sells $5,000 photographs, and this year she has booked 4 days in the hide. What is Karen's mean revenue from her first day in the hide? Okay, there's a lot going on in this question, but I'm confident that you'll be able to work through it. So let's first establish what her lambda is. So she said that last year she got 2 shots. So 3 days in the hide, and she got 2 shots worth $5,000 each. So in other words, her expected value, or the expected number of shots per day, in this case, she said that this is regarding as typical for this time of year. So what we would expect is we would expect her to get 2 shots in 3 days. Nicely, if we do 2 divided by 3, it gives us our number of shots per day. And to the extent that she only sells $5,000 photographs, we can just take the expected number of shots in 1 day of 0.66 times the value of $5,000 to give us an expected revenue for the first day in the hide to be $3,333.33. Okay, why are we using lambda here? Well, in this case, we're dealing with number of events in a given period of time. So we should be thinking Poisson distribution. We're talking about the mean revenue, which is just the average number of shots, the expected number of shots times the sale price. So our lambda 0.666 continuing times 5,000. Okay. What is the probability of getting 2 or more $5,000 shots on the first day? Really, what this question is saying is what is the probability of getting 2 or more photos on the first day, considering she only sells $5,000 photos? Well, we can go to our Poisson distribution here. So the probability of 2 or more, so the probability that X is greater than or equal to 2 is equal to 1 minus the probability that she only gets 1 shot minus the probability that she gets no shots. So 1 minus the probability of 1 shot is equal to e to the power of negative 0.66666 times 0.66666 to the power of 1 divided by 1 factorial. And e to the power of negative 0.66666 times 0.66666 to the power of 0 divided by 0 factorial. Nicely, 0 factorial is equal to 1. So we do not have an undefined quotient to deal with, so we don't need to worry about that. So the probability that she gets greater than or equal to 2 shots is simply equal to 0.14428. Importantly, this is more than 2 shots on the first day, right? So this is why we have our lambda of 0.6666666, right? Initially, as we calculated before, it was 2 shots in 3 days, which is equal to 0.6666 shots per day, right? Okay. What is the standard deviation of her revenue from one day? Well, the standard deviation for one day, so the standard deviation of our lambda when we're dealing with a Poisson distribution is simply equal to the square root of our expected value, or the square root of lambda, because in Poisson distributions, we have this unique thing where the variance is equal to lambda, which is equal to our expected value. This is just for Poisson distributions. So our standard deviation of the number of shots she would get in one day is equal to the square root of 0.66666 continuing, which gives us a standard deviation of number of shots to be 0.81465. And then from there, we're talking about the standard deviation of her revenue. Well, we're just going to do standard deviation of the revenue, standard deviation times 5,000, right? If you go back to previous lectures that you've done the standard deviation of AX is equal to the absolute value of A times the standard deviation of X. That's effectively what you have here. The standard deviation of 5,000 X is equal to 5,000 times the standard deviation of X, right? You remember that from previous lectures. And if you don't, you can watch one of my videos on YouTube on multiplying constants to random variables. That's there for you to review. I'm just going to highlight here that if you only carried 4 decimal points, so you did 0.6666, what you would get is $4,082.28 versus if you stored 2/3 in your calculator and you carried that through, you would get a difference here of 20 cents. So just important to
be mindful that you can get some rounding errors. It's only a difference of 20 cents, so it's not that big a deal, but just be mindful of of what rounding can do to your final answer. Okay, what is the standard deviation of a revenue from the 4 days? Well, we're going to first revise our value for lambda, because we had initially had a value for lambda to be 2 shots in 3 days. And when we did that per day, lambda is equal to 0.66666 continuous shots per day. But now, instead of dealing with 3 days or 1 day, we're dealing with 4 days. So we have to revise our expected number of shots. So that's what we're doing here. So A times lambda, so the A times our EX is equal to 4 times 0.66666, which gives us the expected value of 4x to be 2.66666. Our standard deviation is equal to square root of 4 times 0.66666. So this gives us a value of the standard deviation of 4x to be 1.63299. So our standard deviation of 4 days of revenue is standard deviation of 4x times 5,000, which gives us a standard deviation of 4 days in our 4 days of our revenue here to be $8,164.94. Okay, in this case, yeah, we'll just leave it at that. Okay, use the coefficient of variation as a measure of risk. How much more risky is 1 day relative to 4 days? Well, the coefficient of variation of 1 day is equal to the standard deviation divided by the expected value. So we had our standard deviation of our revenue here divided by our expected revenue. So we got a coefficient of variation to be 1.2247. And then we had our standard deviation of 4 days of revenue and the expected value, which is $13,333.33, right? This is just simply taking 2.66666, multiplying it by 5,000 will give you, right? So 2.6666 times 5,000 is equal to 13,333.33, which gives us a value of 0.61237. So therefore, it is 2 times as risky to go for 1 day than it is for 4 days, right? Meaning, because we can do that because they're telling us here, use the coefficient of variation as a measure of risk. Well, 1.2247 is twice as big as 0.61237. Okay, finally, the return charter flight from Winnipeg, where Karen lives, cost $1,200. How much net income can she expect from the 14-day trip? Well, again, net income is revenue minus costs. So we can calculate the revenue, right, to be the expected value of 4x times 5,000 minus 4 nights in the Hilton at $200 a night plus the cost of the flight, which we're told to be $1,200. So we get $13,333.33 minus $2,000, which gives us a net income of $11,333.33. Okay, so that's going to conclude the review session for today. If you joined late, remember that you can find this video tonight on YouTube. If you subscribe to my channel, You will get a notification once it's uploaded. It may take a little while because it's been almost 2 hours. So if you go to @AndrewScarf on YouTube, you'll find my video from today, as well as a bunch of other study videos to help you either with business analytics or statistics. So I hope you find them helpful. Otherwise, I hope you found today helpful, and I'm going to stop recording and I will tell you more about what's coming next.